we're jumping into something pretty wild. The sheer amount of data you could pack into just 1 liter of water.
Yeah, if that water is set up for DNA storage, that is.
Exactly. And we're asking, can this actually solve the massive information overload that's coming?
Well, that overload, what some call the archival data crisis, it's definitely speeding up. We're talking about the global data sphere hitting 175 zettabytes soon, like by 2025.
175 billion terabytes.
Wow. And the scary part is looking out to 2040, the forecasts show we might need, well, maybe 1,000 times more storage than we'll actually have.
1,000 times. That's the zettabyte gap people talk about.
That's the one, a huge gap.
Okay, so enter DNA digital storage, DDS. It's got these two killer features, right? Stuff that hard drives and tape just can't match.
Absolutely. First, it lasts practically forever. We're
Yeah.
talking potentially thousands of years for data preservation.
And second, the density. It's just mind-boggling. What's the theoretical limit again?
The physics suggests something like 10, 20 bits in a single cubic centimeter. It's astronomical.
Okay, but you're saying the real limit isn't physics, it's biology.
Yeah.
Or engineering.
Yeah, it's more bioengineering. The practical limit today is just how much synthetic DNA you can safely dissolve in water and still get at it reliably.
And that limit is?
It's currently around 3 grams per liter. That seems tiny, right?
3 grams. Yeah, sounds like nothing.
But here's where it gets interesting. Estimates suggest 1 gram of DNA, properly encoded, could hold around 455 exabytes.
Hold on. 455 exabytes per gram. And a zettabyte is 1,000 exabytes.
Exactly. So you do the math. 3 grams in that liter.
That means, whoa, 1.365 zettabytes in 1 liter bottle.
Theoretically, yes. A zettabyte in a bottle. It confirms DNA is absolutely a zettabyte scale technology.
Okay, but that's theoretical. What about practically with error checking and all that?
Right. You always need redundancy, error correction codes, metadata. Groups like Microsoft Research factor that in. Even then, that 1 liter could still reliably store over 61 exabytes of usable data. Still massive.
So walk us through the basics. How does it work? We're turning computer zeros and ones
into the ATCGs of DNA, the 4-letter code of life.
Which gives you more density than binary right off the bat.
Instantly doubles the potential states per position, yeah. And the water. That's key for actually using the stored data.
How so?
Well, the liquid solution enables random access. Think finding a specific file instantly, not like winding through a whole tape.
So
We use something called PCR primers. You can think of them like tiny address tags or bookmarks.
you send in the tag for the file you want.
Exactly. And the PCR process, the polymerase chain reaction, it finds and copies only that specific chunk of DNA data you asked for, amplifying it out of the whole liquid mix.
Clever. But
Yeah,
there's always a but, isn't there? Storing it in water must have a downside.
it does. A big one. Water lets you do that fast PCR access, which is great.
Yeah. But
It drastically reduces that amazing longevity. DNA in water isn't stable for millennia. It becomes more like a medium-term cache.
so for truly long term, like centuries-long archival.
You need to get the water out, dry the DNA, stabilize it. It's a process called lyophilization that gives you the incredible lifespan, but you lose the easy random access of the liquid state. It's a trade-off.
Okay, so we have the potential for zettabytes in a bottle. We have the mechanism. Why isn't this everywhere? It must be the cost.
That's the elephant in the room. The feasibility barrier right now is mostly cost. And speed, too.
Give us the numbers. How bad is it?
Well, think about standard magnetic tape for archiving.
Yeah.
That's maybe, what, $15 per terabyte? Pretty cheap.
Yeah. And DNA synthesis, the writing part.
Current estimates put it around, brace yourself,
Yep.
$800 million per terabyte.
800 million per terabyte.
Yep, millions of times more expensive than tape. It's just not viable for large-scale use yet.
And it's slow to write, too, right?
Painfully slow. We're talking maybe 1 megabit per second throughput for writing. Far too slow for the kind of data volumes industries need to handle.
So what's the plan? How do we fix that cost and speed?
A lot of R&D focuses on shrinking the synthesis process, moving it from lab machines onto cheaper microchips, maybe using new electrochemical methods. That's for the writing cost.
And for reading?
Reading is actually much cheaper and faster thanks to advances in sequencing. And clever software for decoding is helping too, cutting read costs by, 20, 25% in some cases already.
Mm.
but writing is the main hurdle.
Right. So to sum it up for you listening, we have this incredible potential, 1.3 zettabytes, theoretically fitting in a liter bottle.
But right now, the tech to actually write that data is millions of times too expensive and way too slow.
It seems almost paradoxical.
It is.
Yeah.
But here's something else to think about, a sort of final thought for you. Even with today's massive costs, life cycle assessments, looking at the whole environmental footprint from manufacturing to disposal, they actually show DNA storage could be far greener long-term than hard drives or tape.
Really? How?
Lower greenhouse gas emissions, less energy needed over its lifespan, even less water used overall compared to constantly manufacturing and running current data centers.
Huh. So the provocative question is...
Exactly. If DNA storage is ultimately the more sustainable, more environmentally friendly option long-term, how much will that factor into driving the investment needed to finally close that huge cost and speed gap?
Yeah.
What's that green advantage worth?